I'm here to talk about logging infrastructure at Pinterest, and I'm sort of co-speaking with Yu Yang, who's actually built most of this. And we're also going to follow up with some of the things that we've done to manage log quality. So this is the agenda. So just a brief overview of what Pinterest is, and like a deep dive into our logging infrastructure, and then some things that we have done to manage log quality, so softer aspects of how do we make sure that the data that we are collecting is actually of high quality, and then we can get into the questions part. So start with what is Pinterest, right? I don't know how many of you use Pinterest. What we think of Pinterest is what we call as a discovery engine. So it helps you find interesting things. And so when we say that, people ask, like, how is this different from Google? So this is like, hey, I mean, if you have a question, if a fact-based question, like what's the weather in SF today, and you can type in keywords in Google and gives you a really nice answer, and that solves your sort of question. Another fact-based question, what's the central limit theorem? Again, Google does a great job. It basically retrieves the actual answer for you, so you can actually like go off and read it. Not bad, right? I mean, this is really interesting stuff, and Google has built an amazing search engine over the years to actually solve these kind of problems. But if you have this kind of question, what should I cook for dinner today? I mean, if you can enter these keywords in Google, I don't think Google is going to answer your questions, right? So this all depends on your personal taste and what you like, and sort of this is something that Google is not aware of. Similarly, if you're interested to discover your own style, like what kind of clothing or accessories should I buy, or actually what am I resonating with? Or where should I go this summer, right? So these are questions that are very personal to everyone, and there's no one definite answer, and this is where I think traditional search engines like Google and Bing fail. And this is the discovery problem that Pinterest is trying to solve. And how do we solve this? We start with this one object. This is a pin. This is a representation, digital representation of a real world object. So in this case, this is a watch. And a pin comes with like a picture and some description, a title, and it is associated with a collection of other pins. So in this case, this pin belongs to a collection of watches. This is a collection of watches that I'm pinning on Pinterest, which means I'm actually telling Pinterest this is my taste around watches, right? And then all of our users, I mean, we have millions of users doing the same thing and creating these pins, curating these pins and into various collections. We take all of this data and apply algorithms to create a set of recommendations for our users to actually go and discover new things. It's not new. I mean, companies like this have done this before. Amazon, if you've gone to Amazon, it actually shows you recommendations of what you've bought before. So we apply the same kind of algorithms. Obviously, like we have a lot more interesting data. We have a lot of image data to process as well. So, and then we create this feed. This is a feed of recommendations that our users go and see when they come to Pinterest. And we are constantly trying to improve the relevance of this feed to make sure that we're actually serving the right quality of recommendations. And behind all of this is data, right? I mean, we have like collecting huge amounts of data, both the actual data around pins, but also a lot of activity data. We rely on like user feedback. What are users repinning? What are users clicking? What are users searching for on the site? Right, so we collect all of this data and then make it available for processing and power both insights, like to run our experiments to make our decisions, but also more importantly for our products like recommendations, search, things like that. So at a high level, this is how our data architecture looks like. We have thousands of web servers, basically, which our clients talk to for both sort of like logging activity data and also for just general sort of keep retrieving the recommendations. And then that we run this custom logging agent called Singer, which Yu Yang is going to talk about on all these servers, which basically collects all of this data and writes to Kafka. So we've been working with Kafka for a couple of years. We've tuned a lot to make it run scalably in the cloud. So we're going to share some of our experiences doing that. And once the data goes into Kafka, then it has like kind of this Lambda architecture way of two-way of processing. The batch pipeline basically copies the data from Kafka into S3. So we use S3 as our data warehouse, this is basically where we keep all of our data. And from there on, we use Scalable, which is like a Hadoop as a service provider to run our, basically process our data. So they provide us with Hadoop and Spark clusters. So we then run our ETL jobs to munge all of this data. We've built some custom tools to manage all these ETL workflows. We've open sourced this workflow management system called Pinball last year. And then all of this data then goes into the different things. So essentially, some of this data is going into the product directly as recommendations, and then it is going into our analytics system called Penalytics that helps us to look at business metrics every day. It helps. This data is also powering our A/B testing dashboards, and then it also goes into Redshift as an aggregated form for our analysts to query. And we also have the real-time pipeline. Right now, we're using Storm. We're actively investigating a stream processing engine that replaced Storm. Personally, I actually led the Storm project at Twitter, so I know both in the pros and cons of it. I know, and then there's a talk today. Karthik is going to talk about the Twitter Heron, which is the Storm v2. So, if anyone is interested. Anyway, and then we have the real-time pipeline. Then basically takes the data from Storm, and we've had this custom event processing engine called Stingray, which we use for a lot of filtering and action taking and processing rules on top of event data, mainly for spam detection and other things like sending emails and notifications. This is not open sourced yet. We might be doing that sometime this year, and then that actually also serves the data into the product. So that's kind of a high-level overview of the data architecture. With that, we'll go into the logging infrastructure, and I'll hand over the mic to Yu Yang to go over it.
So hello, everyone. So I'm going to continue talking about the logging infrastructure we built at Pinterest. We want to share our experience here and collect feedback from the community, and also improve our logging infrastructure. Okay, cool. So first, let's talk about requirements for the logging infrastructure. What are logging infrastructure required? And there are a few high-level requirements about the logging infrastructure. First is availability. The infrastructure should be always up and running, right? And no downtime allowed. Second is about the minimized data loss. Zero data loss. Of course, the distributed system is not perfect. There can be incidents, etc., but we want to have minimum data loss through the pipeline. The third part is the horizontal scalability. So the traffic can go up and down. So to minimize the efficiency, we always want to maximize the efficiency, right? We want to have the best utilization with our computation resources and the storage resources. Meanwhile, so how can we do the horizontal scalability when the traffic ramps up, right? And the system should continue works when the traffic goes up 10 times, right? The fourth bullet is the low latency. The event should reach should be available for consumption within seconds, right, after it's being logged, reach our server side. The last part is, I think, is also very important for us is the operation overhead, right? The system should be up and running with minimum human intervention, and so streamline this is especially important for us, which has only limited amount of staff for running the system. So let's dive deep into our logging infrastructure. First, let's look at the very high-level overview of our infrastructure. So the logging infrastructure is a very high level. It's very simple, right? It's just collecting the logs and putting the logs into storage for later consumption. And it has primarily 3 blocks. One is the app server, where the services are running, and we're collecting all the events, all the messages we collect from the client apps. The second part is a message transportation. Here we use an open source system called Kafka. That's is a very nice horizontal, scalable, reliable system to do the message transportation. The third part is also the data transportation out of the message queue, like Kafka, right? Because we have a huge amount of data coming in every day, and the message queues can only cache the messages for a limited amount of time. We need to transfer the data out of the message queue and stored in the cloud storage. How can we do that reliably and efficiently? That's also a challenge for us. Currently, also we described briefly at the Pinterest logging scale. Currently, we have tens of thousands of hosts running in the cloud. We are only running in the AWS right now, and we are logging more than 120 billion messages per day. And we use Kafka as our central message transportation hub. And currently, we have the cluster size about more than 500 brokers. And we have developed some in-house technology for logging messages, transporting messages from our app servers to Kafka, and also transporting data from Kafka to S3, which is our source of truth for the downstream processing. So first, let's retrospect the evolution of our logging infrastructure. So this diagram shows the V1 version of our logging infrastructure, where we were using, this is about 2 years ago, when we were using Kafka 0.7, and when Kafka doesn't provide the replication for the messages. And this infrastructure is quite simple. When a message reaches our server side, and the server just directly writes the message to a Kafka. And then Kafka, we have a daemon we call the data uploader, just running there and periodically uploads the data into S3. And from there, also we have, of course, the real-time consumption services from Kafka. And from the S3 part, and we have the batch processing kicking to do the further data processing. So, and this diagram is very simple. And because of there is no data replication, and we just need the data uploader running on each of the broker to upload the Kafka messages, or Kafka files to S3. From there, we can have the conversion job to convert the Kafka logs into all the downstreaming data that the further processing is needed. So there are a few problems with this, this kind of the pipeline. The primary problem is the data loss. The Kafka brokers can go down unexpectedly. If the broker fails, and basically because there is no replication, all the data on the broker will be lost if the data has not been uploaded to S3. The second is because we have the application servers write directly to Kafka. If there is high back pressure, and because we do the directory writing, we need to queue the messages in in-memory buffer before writing to Kafka. So if there is a spike of traffic and there is high pressure, back pressure in the message queue, and the message queue got overflow, there will also be data loss. And the second part is about operability. Because of the Kafka brokers can go down at any time, and also because of the limitations in the implementation of the Kafka consumer, etc. And each time this broker goes down, and we need to replace the broker, and then we need to also restart or do rolling restart of all independent downstream services to make sure that they pick up the right broker list. And that's add a lot of operation overhead. So because of this, and we switched to the later versions of Kafka that supports replication, and starting with the Kafka 0.8, right? But with challenges with the Kafka that supports replication, there are also a few challenges. First is because of the introduce of the replication, now a message can have multiple copies, lives in different brokers. And with this, our original approach of using data uploader to upload the data to the Kafka, to S3 itself will not work because you don't know which broker is a leader for the topic partitions, and the topic partition leaders can change frequently. A second part, and we can no longer randomly pick up a broker and write to. And when we try to write to Kafka, we need to know the leader of the topic partitions, and we also need to handle all the corner cases of the when the Kafka broker is unavailable, or when a few topic partitions become unavailable, or in the middle of the leader election. So, and the next slides, I will show you And so here is our logging infrastructure, the V2, in which we add a few building blocks, which shows in the blue box here. First, on our app server, we changed the mode of directly writing to the Kafka brokers. We have our services write messages to local log files. From there, we have developed an in-house logging agent we call Singer that reads the log messages and uploads the logs to Kafka. The second piece that we developed is the data transportation service that we developed two versions. First version we called Secure, then second version we called Merced to move data in volume from Kafka to S3. And the third block that we added is the data sanitization, because the first part, the Singer and the Kafka and the Secure part, the whole pipeline supports at least once message delivery, right? There could be duplication if there could be duplicated messages introduced along the pipeline. And also there could be data corruption introduced because of the incorrect schema or because of the some users just unintentionally write some bad messages into some pipelines, etc. So as a final stage, we introduce the data sanitization, which sanitizes the data and before doing the further processing. So this is a very high-level overview of our logging infrastructure. And the latency right now from the event reached our endpoint to log to Kafka is within seconds, usually under 5 seconds. And from the moving data out of Kafka to S3 part, we can do either hourly ingestion or the daily ingestion. So it depends on the requirements of our customers. So at the same time, we also use this with Kafka 0.8. We're also using Storm and Spark. We are also exploring Spark streaming to do the real-time data processing for our data pipeline. Yeah. So in the next few slides, I will dive deep into the Singer and the Secure part, and we are also talk about our experience of running Kafka reliably in the AWS public cloud. And first, let's talk about the logging agent part, right? The Singer, so our logging agent. The logging is at very high level. It's very simple, right? It's just write messages to a log repository like the Kafka, right? It's very simple, but there are also a few challenges that we face. The first is the reliability, right? The logging agent should be very reliable, always up and running, and keeping uploading logs to the message queues. The second part is about the high throughput and low latency. The logging agent should be high efficient and can upload a huge volume, large volume of data, and with the minimum amount of the latency to the message queues. And also, we need to be highly efficient to minimize their CPU footprint and also the memory footprint in the hosts. And another requirements that coming from our customer is it needs to support various log format, because we not only log logs from the service that develops at Pinterest, but we also need to upload the logs from various third-party softwares. Also for all the open source, all the logs from the open source softwares. So we need to handle various format and to do and support plugins to do the message filtering. Another part that's important is we need to make sure there is a fair scheduling, so that the logging agent needs to upload the logs in low latency, not only for those logs pipelines in large volume, but also for those low volume topics, right? How do we guarantee the fair scheduling is also an important part. So let's look at the logging agent of Singer. The Singer is just a logging agent we developed at Pinterest, and it's the high-level concept is very simple. And it's just the application servers and using some client library to write logs in either thrift format or text format and to the local file. From there, and the Singer picks up and writes those messages to Kafka or the other message queue systems. So the reason we choose this architecture is the primary reason is try to decouple the various systems. So we want to isolate the logging agent failure from the application failure, application server. So minimize, if the logging agent fails, right, it will not cause data loss. The application server just writes logs to local disk, and the logging agent can still pick up later and upload logs to the message queue. The second part is about we want to decouple minimize the impact of the message queue failures. So if the Kafka is down, and the logs can be still cached onto app servers and can be uploaded later. So with Singer is implemented in Java, and it's a high performance logging agent. We can achieve more than 100 megabytes per second uploading to Kafka for those for the thrift log messages that we have at Pinterest. And it provides a few production environment support features, including the dynamic configuration detection. And because the production teams can continuously adding or removing configurations, adding new pipelines or remove existing pipelines from the environment. How to handle this and cases and minimize the operation overhead is an important part for the logging agent. The second part is the second feature is adjustable logging latency. For some log streams, we may need very low latency. For some other, while at the same time, for some other log streams, it may the customer may be fine with saying 30 minutes latency. So we have all the configurable parameters that allow Singer to tune the various size like the logging latency, batch uploading, etc., to fit into the various performance needs. The third part, the third feature is the auditing, right? Because we need to gain confidence about the logging. So if the logging agent, how do we know the logging agent is uploading all the full set of data, right? And if some message is missing in the middle of the pipeline, and we should be able to detect and respond faster. So we need end-to-end auditing feature. And the Singer supports the auditing feature so that allow us to do the end-to-end message auditing. The last part is the heartbeat mechanism. Because Singer is running as a standalone process on each of the hosts. If the Singer is down, right, then and if we cannot detect this in time, then the logging will be delayed, or we may face potential data loss, right? How can we make sure we can aware of the Singer logging agent failure and get alerts on time when the logging agent fails on hosts? The heartbeat mechanism helps to prevent this. So with the heartbeat, the Singer writes a heartbeat message to a specific Kafka queue, from where we can do the aggregation and the monitoring and comparing with the hosts, the list of hosts that have already been launched, and alert us on time when some failure happens. And next, I will briefly talk about the internal of the Singer. And Singer is implemented using the staged event-driven architecture, in which we have the divided the logging processing into multiple stages, including the configuration file detection and the log file change events monitoring, and the log file reading and log file writing, and the final one piece is omitted in the block is the network transportation to Kafka. So at the very high level, we just have a few building blocks. We have a log monitoring thread that continues monitoring our configuration directory and to pick up the new configurations. And we also have our file system monitor that continues listening to the multiple log directories and receives sending events to the later processing layer, try to notify that there are new logs to be processed or new log streams to be picked up. And in the log processor part, we have the multiple threads pools to do the parallel processing. we have a set of readers try to read the messages from those log streams, and we also have a set of writers to hook up of each of the readers and of the log stream to write log messages to Kafka. So underneath, and we have another thread pool, a network transportation layer that to parallelize the writing to Kafka. So we break down each batch into multiple small packages based on the signature to each topic partitions so that we can do the parallel writing to each of the topic partition to speed up the throughput. So that's the single part. The next part we will talk about our experience of running Kafka in the cloud. So Kafka is an awesome open source software, and it's very reliable when we're running on-premise hardware. But when we're running in the cloud, there are a few new challenges we faced. One is the brokers can get down unexpectedly because of various reasons. There could be a small-scale AWS outage, or maybe a physical host in AWS is down, and you happen just to have multiple virtual instances running on that host. And there were so many reasons that brokers can go down unexpectedly. The second part is, so the EBS I/O performance can degrade significantly and due to the resource contention. So if you know more about the EBS internal, so the EBS has data volumes, the EBS volumes host on the physical host. And because we don't have control on the EBS volume allocation, multiple EBS volumes that used by our Kafka services may get allocated on the same physical host. And when the load goes up, it ends up multiple EBS volumes can have the contentions, and the performance of the I/O throughput got significantly degrade, and it causes the latency in our data pipeline. And also, because of the, and also, we were using the small instances like the C3x, C32x, or D2x large for our Kafka brokers, while with this, Amazon can collocate multiple virtual instances in the same physical host. So then, if you have the physical host failure at Amazon data center, it may affect multiple virtual machine instances in our cluster, right? And in the replication, with the Kafka replication, if you have 3 replica, while you have all the 3 replica running on the same physical host, and if that physical host fails, basically you lose all the data for that partition. That would be very bad. And the last part is about the faster recovery. So when something bad happens in the cloud, right, how can we recover the service faster and bring it back to the normal states? That's something that is also challenging for us. So, and next slides, we will briefly talk about our experience of this. So our initial setting with Kafka is that we use a C3 2x large plus EBS as our settings because the C3 instances doesn't provide enough local storage. And so we use the EBS as a supplemental storage. But this gives a problem. The primary problem that this gives us is the EBS, the I/O performance degradation, because of the contentions that we have among the EBS volumes. So starting from the early last year, when the D2 instance is released, which is the new Kafka, the new AWS instance that supports local disks, we switched to D2, which allows we use the local disks to avoid the EBS contentions. And also, we use there are multiple instance types in the D2 family. It's a D2x large, D2 2x large, and the 4x large and 8x large, right? And of various size. We choose the smallest instance type to make sure to minimize the data footprint on each of the brokers so that when broker fails, we can quickly transfer all the data to another broker and get recover faster. To address the topic partition, the collocation failure, collocation problem. So we need to make the available zone aware partition allocation. So that so currently our policy is for each topic partition, needs to be stayed on the 3 different available zones. If we find some topic partition is allocated only on 1 or 2 available zones, we need to then have some scripts to move it to some new brokers to make sure we have the available zone of aware replication to make sure to minimize the impact of the physical host failure. The last part in our experience is it's better to have multiple small clusters than just a gigantic cluster. So we deployed multiple small clusters, which only have 20 to 40 brokers per cluster to provide the topic level isolation. So make sure if one cluster has a problem, it doesn't affect the topics on the other clusters. So this is the briefly summary about our experience with Kafka, right? And the next part, we will talk about our data persisting part, right? We will talk about the challenges we have, our experience of transporting data from Kafka to S3 or the other cloud storage. So for the data transportation part, so there are a few requirements that we want to achieve. The first is a strong consistency. We want to have each message to be persisted into the cloud storage exact once. And we don't want to persist multiple times, right, for efficiency reasons. And also, we definitely need fault tolerant. And in the data transportation service, if any of the worker nodes goes down, and this should be transparent to us, and the work should be able to be picked up by other workers and to continue. And we also need to have the event load balancing to make sure we can handle the traffic spikes fine. And of course, the horizontal scalability is one of the basic requirements. The last part, and we also need the configurable, make the system very flexible for various configurations, like the upload policy, and the final destination, and also data retention policy, etc. So based on these requirements, and we developed initially our solution is Scalable, which uses a high-level consumer to read messages from Kafka and relies on the internal mechanism of a high-level consumer to distribute the work across multiple workers. Right? So Scalable has a nice feature. And it has, we use the Zookeeper to keep track of the progress of each worker, of each topic partition. And so we have a mechanism to guarantee the strong consistency. So for each message, we can be persisted exact once. And also, the Kafka high-level consumer provides a nice feature of the fault tolerant. If any worker node is down, and the Kafka client library will be able to detect the failed nodes in the consumer group and pick up, right, have it picked up by some other hosts in the group. And it has a load work distribution, and also we have the configurable upload policies, etc., right, implemented in Scalable. But with Scalable, with the Kafka that uses high-level consumers, and we have a few challenges that when we try to operate this data transportation service at a scale in the cloud. So these are the challenges that we faced. So Scalable uses Kafka high-level consumer, and which is actually the consensus-based workload distribution implementation. The multiple consumers in the group needs to talk to each other and make a consensus on the workload distribution. If there is any failure is detected by some of the some of the consumers, and there is a low workload rebalancing will be triggered. And if the rebalancing is not successful, and there will be another iteration of the rebalancing until another consensus is reached, right, by the consumers in the group. So, but in our experience, and this kind of consensus-based workload distribution can cause trouble in various scenarios. When especially when the data volume is high, if the data volume is high, and also there is a workload consumer group rebalancing, and it can causes lags in the processing data to the final cloud storage. And because we don't have control over the consensus election, right? And there is no way we can, if there is lag, there is no easy way for us to mitigate the problem and catch up. And this is really bad for us. And also, because of this, we try to minimize the impact of the consumer group rebalancing in Kafka by isolated topics into different consumer groups. But then this adds that's more overhead to us on the distributing the workload among multiple topics. And it's very inconvenient for us to add new topics and add new or dynamic add topics or remove the topics from the data pipelines. And also for the efficiency part, the high-level consumer has a client library. The Kafka high-level consumer client library has a few nice features like the group rebalancing, workload rebalancing, and failure detection, etc. But this also adds overhead on the same consuming messages from Kafka, right? So given this, and we improved our data transportation service and evolved into the second version we called Merced. In the Merced, we try to remove the workload distribution decisions that is made by the Kafka client library. So in Merced, we just directly using the Kafka simple consumer, try to have each worker to use Kafka simple consumer to consume data from Kafka. And we employed a master worker approach in which the master reads the configuration files and creates the work assignments. Meanwhile, the workers read the worker assignments and do the actual work from reading data from Kafka and persist it to S3. The master do all the work of saying the dynamic configuration detection, and uploading policy change, or the data retention policy change, etc. Otherwise, the worker just do the simple work of reading data from Kafka and upload it to S3. So, and the master and worker, to minimize, to decouple the dependency between the master and workers, we use Zookeeper as a broker for the data communication. The master just write all the assignment information to Zookeeper and the worker can pick up. And also, the workers write all this the progress, their status report, etc. to Zookeeper, so that the master can know the worker status. So we have deployed the Merced service has been in production for months and is transporting almost all of our data from the Kafka to S3, and we also built some nice UI to allow us to immediately see the progress of each topic's partitions to make sure. And if something bad happens, we'll get alerted based on the various metrics we are monitoring. So that's all the building blocks we have built in the logging infrastructure part. Next, I will hand back to Krishnan. He will talk about the log quality.
Thanks, you. So one of the things that we wanted to make sure is, because we rely so much on data, at the end of the day, we are kind of building a data product. We need to be really, really careful about ensuring that the data that we're collecting is of high quality. So we made some investments to actually both tools and processes and culture-wise to actually make sure that the log quality is actually high. At a high level, we look at log quality as two things, right? One is reliability, like the completeness aspect. Are we collecting all of the data? And so that a lot of the logging infrastructure that we've built up is geared towards that. So essentially no data loss and availability of data in reasonable amount of time. And then the other aspect is the correctness of data. Essentially, this is where requires some human interpretation, and there's a lot of things that can go on. Developers who actually ship features may actually forget logging data or may break existing logs, or in some cases, like our ETL jobs that process the data could actually be doing something incorrect. So a lot of these changes are hard to find. So some of the challenges is like, if you're a feature developer on iOS or Android or a product engineer, instrumentation is like an afterthought. You don't really think about it while you're actually building the feature, right? Just before you actually try to launch it, you kind of sort of think about it. The other thing is features can be shipped, breaking, sort of logging, or without even adding new logging. So, and if a release goes out to the wild, I mean iOS or Android, and it just takes weeks for the data to be corrected, because like for weeks for it to be actually upgraded. So even if we release a dot release, it'll take a lot of time for it to actually catch up. And unlike code quality bugs, data quality bugs are hard to find. So a developer can actually may introduce a subtle bug in logging that sort of changes our DAUs, and sometime like maybe a month or a couple of months later, an analyst actually looking at it and says something like finds a discrepancy, and it just makes it really hard to actually go and fix it and patch it. So in order to do that, we started with, first thing is introduce like tooling, right? Like as engineers, we wanted to make sure that can we actually automatically detect things. And so one of the things that we built out was this tool called Firefly, which essentially has a few components to it. At a very basic level, the first version was just hook up to Kafka and inspect logs like a real-time grep, right? Like basically like introduce some keywords and inspect the logs. And then we later on worked on the version 2 of it, which is to add these sort of what we call real-time checkers. So these are the invariants that we actually make sure that they're always respected. So you can call them as data unit tests in some ways. So we then say like, okay, before every release, we try to make sure that we play with the app and run Firefly on all the events that came out of that sort of pre-production build, and ensure that the logging changes. There were no regression loggings and things like that. And then we also built up our anomaly detection tooling to ensure that hey, like, are the metrics that we are computing, are there anomalies in it? So this will also help us to catch things that if there are bugs in the ETL pipeline or sort of data ingested. So the way we've done it essentially is very simple. So we take a look at like the last few weeks worth of data and assume the data is normally distributed, and then we took a look at today's data and see like what's the p-value, so how much statistically it is deviant from the previous data. And so if the p-value is less than some threshold, we look at all those metrics that actually have the p-value less than the threshold and mark them as anomalies. And so this actually helps us to find periodically. So every day this email goes out to a bunch of people in the company that care about data, and they look at it, and we actually segment it to like, hey, like team-based or individual-based. And so essentially so that they can actually look at, in this case, this is actually showing our weekly active repinners metric has some anomalies in it, and actual values are hidden for obvious reasons, but you can actually see how the format looks like. So how did we do? So this kind of anomaly detection actually helps us find various things. There are two things, like expected changes and unexpected changes. So someone is running an experiment, and an anomaly that they find is actually expected. And obviously things that we don't expect, we should be able to find there. And also sort of user-facing and non-user-facing. So things like when we introduced this feature called users can follow interest in addition to other users on Pinterest, then we actually saw this sort of interest follows went up. And things that we don't expect to see, like when tracking changes that basically get detected because of some unexpected logging changes. However, one thing that we found is no matter how much tooling and automation that we do, there needs to be a manual step towards ensuring logging data. So we basically introduced this culture and process around auditing logs just before application release go out. So manual audits are not scalable. They have their own limitations, but they do catch very critical bugs. So we've introduced this repeatable process of like two things. One is a regression audit, ensuring that we basically make the core logging actions. We do core logging actions, and so like using the tool to verify the output of those actions, and then new feature audit. So this is sort of a little difficult in the sense that when feature engineers are creating a new feature, they need to think about instrumentation. They need to sort of sit with a business analyst or a data engineer to ensure that like, hey, are the events that I'm producing are actually the right kind of events that will help you measure my feature, and then sort of and then logging them and actually verifying verifying if the logging was done correctly. So some of those things actually help us. So it's like a bunch of tooling and some process, and that sort of help us on a day-to-day basis. So in terms of summary, some of the things that we found were investing in our logging infrastructure has really helped us, right? So I think we've invested it in pretty early on. We focused on things around like minimizing data loss and completeness of data. We've invested on Kafka. We had options being on AWS to use some of the AWS services, but we picked Kafka, and it actually sort of helped us. Kafka has matured a lot, and all the investments in time that we've put in to tune it to get it working on the cloud is actually paying off. And data quality is not free. I mean, that's something that we've learned hard way. When I joined Pinterest, we had releases going out with no user ID logging for some features, so we had no insight into how those features were actually doing. So it's not free, so one needs to pay attention to it on a regular basis. And automation tools get you a long way. Pre-release and post-release automation tools to detect logging bugs. And the hard part is data quality is actually a really difficult problem compared to code quality, and that's one thing that I've kind of learned in the last 2 years. And then the other part is just culture building. So I think it's just not one team that's responsible for this thing. We need to put everyone, sort of the mobile engineers and sort of the product managers and the business analysts. This should be like a common sort of effort to ensure that data that we're collecting is of high quality, and that's something that we've tried to do at Pinterest. So that's kind of the end of it. Yeah, if you have any questions, by the way, we are hiring, so if you're interested, you can reach out to me or Yu Yang, and if you have any questions, I'm happy to answer, or you as well.
Hi, this question is for Mr. Yang. Basically, you mentioned in the Singer, the heart thing and the errors relation. Can you a little bit deep dive in that? The heartbeat and the Singer.
Oh, so the question is about the heartbeat in the Singer mechanism, right? So, and the heartbeat message is, so we implement the feature in Singer that periodically, just it's a configurable parameter that we can, every specific interval, saying 10 seconds or 1 minute, whatever, you send a message to a specific Kafka topic. From there, so we can have a downstream consumer and just continuous reading from that topic and aggregate all the information and check. We also have a separate list of hosts that's running. So that's updated every 5 minutes, something. Then we can compare these two lists to see where the process is not running. So then we have some automated recovery through another monitoring system, for instance, Nagios, whatever. Yeah.
I was wondering if you could talk a little bit more about the sanitation piece that you mentioned. I didn't exactly understand if you were enforcing the strong consistency via that piece, or if that was part of Merced. And then also, if you're doing the sanitation in that way, how you ensure that your batch analyses are actually only operating on the sanitized data?
Oh, good question. So the sanitization part, so let's retrospect the Singer Kafka Secure pipeline, right? The Singer itself only guarantees at least once delivery, because if the Singer tries to load a batch to Kafka and it fails in the middle of the uploading, right? And it may retry again, but in the retried part, and part of the batch may have been success in the previous attempt, right? So this part introduced is where most of the duplication is introduced. The Merced part is guarantees exact one-time delivery is from the read message from Kafka. For each message you read out of Kafka, we can guarantee you just put it once into S3. But for the original part, then it's not. So, and the sanitization part, we run this as a Hadoop job on our Hadoop batch processing part. So we have a workflow that read the raw data and sanitize the data and put it in the new location for the downstreaming processing. So, yeah.
So I'm interested in the audit logging process of Singer. how do you audit those and how do you upload those? Those go with Kafka as well?
Yeah, great question. So the auditing part is we implement this this way. So, and for Singer internally, it's to the batch uploading. For each batch of messages, it's writes to Kafka, and we create another audit message and write to a separate topic saying, oh, the audit topic. Now this is for this on this host and when. And we write this how many messages to another topic, etc. So then we can have an aggregated view. So have our same workflow running either hourly or daily to compare the end-to-end numbers to see the differences. Yeah.
So logging only really matters when somebody does something about the fact that there's a problem. So are you planning on building, or do you have some sort of like, this thing is a failure and it should be assigned to this person, and like tracking on whether or not they're going to, we're building something similar right now, and I'm like struggling with how do you define which errors go to which teams, and then afterwards, how do you know whether they've resolved it?
So the question was, are you talking about logging in the context of application logs where the server logs errors, or is it in the context of general logging?
So if you've like identified errors,
Sure.
who has to fix them and how do they get notified? And so that's sort of a layer on top of that.
That's a great question. So as I said, like so basically, if you find any data quality issue, it can range from like whether the metric or how the metric was computed, to the way if the data was logged correctly, or was there any sort of problem in the pipeline, right? So generally the investigation, so someone could actually point out a bug. It could be a sort of on the product side or a business analyst, and it comes down to us to actually carry out the investigation. But as we go into places, for example, if we do find that this was actually a problem in the mobile, in a particular mobile release where so we forgot to log the app version correctly, so we were not measuring the DAUs. So then we basically follow up with the mobile team, and then that's their responsibility to actually fix it. But the investigation is actually carried out by our team, the data team. Yeah.
For the recording, thanks. You guys introduced the Singer for data failure because of Kafka, and I saw in your architecture you have a spam detection afterwards. Do you guys do filtering in Singer? If it is the case, why spam detection is done later in the stage, not in the previous? Then my second question is, have you guys evaluated Kinesis versus Kafka? Because that will solve your both problems, I believe, based on my understanding. I want to ask third question, forgot, sorry.
Sure. So the first question was like, why do we do spam detection in a different service than actually Singer, right? So the way we look at it, I mean, if you've looked at the evolution of the architecture, you see that there are a lot of decoupling going on. So that's been our mantra to the two things: so separation of concerns, have individual teams work on what they need to work on, and separate out the abstractions in a clean way, and also to reduce the failures of one system avoiding the other, right? Number two. So the spam detection system has a lot of things going on to it. So we basically have we have these non-engineers, like the operations people, the community operations people that react to spam on the site, and they come up with like, hey, this new kind of spam is coming, and they encode a new rule. And so that rule has to be processed on an EQ. So essentially the system is built in a way that it can read from Kafka, or later on it can read from anything else, right? So it doesn't really need to happen on the web service. If you think about Singer is actually like a logging agent that's actually collecting. So one way you can actually transport the rules to be detected at that place, but it's just much more convenient to actually do it at the level where you're reading from Kafka, because you can actually apply the same rule on historical data, because for oftentimes we may detect a new spam rule and say like, oh, the same system that applies rules on the real time should also apply it on the historical data. So that just makes it very convenient. And the second question was why not Kinesis and why Kafka? So I think, if I remember correctly, when we started introducing Kafka, I don't think Kinesis existed in Amazon, and we were already on Kafka. But that doesn't prevent us from looking at Amazon. Our philosophy at Pinterest has been to be as cloud agnostic as possible, and as we try to scale our business, we use Amazon mostly for EC2 and S3, right? And except for Redshift, which is the only other Amazon service that we use, we don't use anything else. So that actually philosophically allows us to is like either build in-house or use open source, right? Versus using an Amazon service, because that allows us to like move to a different cloud in the future.
Singer is a EC2 instance or is just a homebase?
Singer itself is a process. Another reason that I think is we don't use Kinesis is efficiency reasons. So comparing to using Kinesis, and it's more efficient, so we just deploy the Kafka message systems and operate everything by ourselves. Yeah.
One more.
Yeah, I have a question regarding the format. So it looks to me using Mosi or SQL to reading from Kafka and writing to S3. So what kind of format are you choosing? Also, second question, are you guys considering like upgrading to Kafka 0.9 or 1.0 or something?
So the question is first about which is the format we process to S3. The second is, are we considering upgrading Kafka to 0.9? The first question is, right, there are multiple formats we can support. One is the sequence file, and we are also considering Parquet right now. And with the sequence file format, we are evaluating various compression algorithms. Currently, we are using the gzip compression to minimize the storage footprint. Yeah. And for the upgrading part, right, we are considering upgrading to 0.9, which came out late last year, and maybe in Q2. Yeah, I think so, because we are also evaluating Kafka streams to do the streamline processing thing. Yeah.
Thank you, guys.